A small airship hangs inside the pale cloud deck of Venus, no runway below it and no safe ground to fall toward. Mars looks easier because the picture is simple. Boots in red dust, a rover track, a habitat on solid ground. Venus seems to lose at once because its surface is hot enough to ruin ordinary machines and buried under crushing pressure. That surface is not easier than Mars. It is the hard stop. The strange part begins higher up, around 50 kilometers above Venus, where pressure and temperature move into a range engineers can discuss, while the planet below remains lethal. If humans never try to stand on Venus, the comparison changes. The floating machine turns the question from surface against surface into platform against planet, altitude against ground, and the mission architecture that follows. By the end of tonight, you will understand why the most impossible-looking planet in the inner solar system can still force a serious comparison with Mars. If you enjoy exploring questions like this with me, subscribing to the channel helps others find them too. Sharing the video helps even more. Let's begin. A boot print in red dust is easy to understand. The mind knows what to do with it. Someone has stood somewhere. Weight has pressed into soil, leaving a mark that points backward to arrival and forward to the next step. That is why Mars wins the first picture before any spreadsheet appears. Mars gives exploration a floor. A lander can arrive and become a fixed point. Rovers leave tracks that still mean something tomorrow. When a drill bites into rock, the sample has an address. When a solar panel opens on the ground, it becomes part of a site rather than part of a vehicle fighting to remain suspended. This is more than romance. A surface changes operations. Picture a small Mars camp after the first cargo deliveries. One shelter has a door. A rover waits nearby. Power runs out toward panels at the edge of the site, while storage sits close enough for a suited crew to reach it. The scene is still dangerous, but it is legible. People can point to a ridge and remember yesterday's route. They can point to a rock and remember which layer it came from. If something breaks, the broken thing is still somewhere in the working ground. That ordinary placement matters more than it first seems. Exploration is partly the art of returning to the same problem with a little more knowledge. A rover finds a target, approaches, backs away, and tries another angle. Over time, those corrections become a map. Human crews would need the same patience. Routes would become familiar. Hazards would acquire names. Tools would need a place to be stored. Mistakes would need a path back into the work. Mars has already shown that this slow learning is possible. Its rovers and landers have not made the planet easy, they have made it knowable. Machines have crossed real terrain there and measured weather. They have inspected rocks and survived long enough for engineers on Earth to learn their habits. A fragile robot waking up on the same patch of ground where it slept is a quiet achievement. It means the planet can hold a working history. A crewed mission would inherit that advantage under far harsher stakes. People would need pressure and oxygen. They would need heat, cooling, radiation protection, and medical backup. Supplies would have to stretch back toward Earth. Yet the basic verbs remain recognizable. Land, anchor, drive, dig, shield, repair, return. Those verbs are not small. They are the operating language of a settlement attempt. Mars is also not being turned into a friendly world. Its atmosphere is so thin that a person outside a habitat would die quickly without a pressure suit. Cold reaches into machines and batteries. Dust can cover panels or creep into joints. Radiation remains a serious design burden because the planet lacks a thick protective atmosphere. Low gravity, about 38% of Earth's, may or may not be tolerable for long human life. No one has proved that a body can thrive there for years. Still, harsh is not the same as unreadable. Ground lets emission accumulate. Equipment can be set down without spending energy to stay in place. Cargo can wait through the night. A damaged rover can become tomorrow's repair task, rather than an object falling into another hazard. Extra shielding can be moved over a shelter as the base learns how to protect itself. Infrastructure has somewhere to gather. This gives failure a different character. If a wheel breaks, the problem may be severe, but the wheel is still on land. When a cable fails, a crew can trace its route across the site. When a drill jams, the machine remains beside the hole it was making. The mission may lose time, power, or science, but the ground keeps the pieces within reach. That reach matters psychologically as well as mechanically. A place can be dangerous and still become familiar. The slope behind the habitat, the route to the rover, and the sheltered side of a rock field become anchors for work and memory. Human beings are good at learning places. Mars, for all its hostility, offers a place in that old sense. Another strength follows from that stability. Mars lets planners break the mission into problems that can be studied separately before they are joined into one architecture. Radiation pushes the design toward shielding and timing. Dust becomes a maintenance problem as well as a weather problem. Low gravity becomes a human health question that can be measured, watched, and perhaps mitigated. These hazards still interact. They do not all depend on the habitat remaining airborne every second. That separation gives engineers room to think. A crew can rehearse a power repair without also solving buoyancy. They can redesign a rover route without changing the fundamental location of the base. They can add mass to shielding and storage in ways a floating Venus platform would have to justify kilogram by kilogram. The planet is hostile, but it allows some parts of the mission to stay put while other parts are being solved. This is one reason Mars feels more real. The horizon suggests distance, but also a path. Rocks suggest science, but also contact. Rover tracks are more than pretty marks in dust. They prove that motion can become memory. A crew looking out from a habitat could see a world that is hostile yet spatially stable enough to learn. Venus in the first picture gives almost none of that. The visible planet is cloud. Beneath it is a surface no ordinary human mission can use as a campsite, repair yard, emergency refuge, or field laboratory. If the destination is the ground, Venus does more than lose to Mars. It exits the comparison. There is no fair way to make the surface case gentle. The result is a fairer starting point. Mars is not chosen by habit alone, and Venus is not dismissed by laziness alone. Each world offers a different bargain before any crew leaves Earth. Mars gives the comfort of a surface, and then charges for atmosphere, shielding, power, and gravity. Venus denies the surface completely, then offers a strange altitude where some of those charges may be lower. So Mars deserves its strongest argument before the comparison climbs into Venus's clouds. Touching the ground is not a cosmetic advantage. Returning to the same rock, the same cable path, and the same shelter changes how crews might move, remember, repair, and survive. If the question is which nearby planet gives humans a place to stand, Mars wins. But that answer smuggles in one assumption, that a destination must be ground. Venus becomes interesting only when that assumption is removed. The ground on Venus is not waiting for boots. Near the surface, the temperature is about 467 degrees Celsius, hot enough to melt lead. The pressure is about 93 times Earth's sea level pressure. Those two numbers do more than make the planet uncomfortable. They move the surface into a different class of engineering problem. The boundary has to be stated plainly. Venus is not easier than Mars, where the rocks are. If the mission means a crew must land on the ground and build there, then drive there and return to a habitat there, the comparison is over. Mars wins. The Venus surface is the hard stop. A base on that ground would not simply need to hold breathable air inside. The outside world would press on it with crushing force while heating every exposed part. Seals would age in heat. Windows would need to survive pressure and chemistry. Electronics would have to work far beyond the comfort zone of ordinary spacecraft hardware. Motors and insulation would be pushed hard. Batteries, wiring, joints, and sensors would face the same punishing environment. Cooling would be especially cruel. A Mars habitat fights cold. That is hard, but at least waste heat has somewhere colder to go. A Venus surface habitat would be surrounded by an environment already far hotter than any human living space. Keeping the inside livable would mean pushing heat out into a world that does not want to receive it. Robotic history shows the scale of the divide. Mars rovers have lasted long enough to turn the surface into a long experiment. They have crossed terrain, studied rocks, endured seasons, and changed plans as new targets appeared. Their endurance should not make Mars look gentle. It should show that Mars allows slow fieldwork. Venus landers achieved something different. The Soviet Venera missions returned real images and measurements from the surface, and those moments remain extraordinary because they happened in such a hostile place. Survival for minutes or hours on Venus can be a triumph. That is not the same operational world as a rover that can wake up, drive, stop, and continue learning year after year. The difference is physical, not cultural. Computer chips rely on signals staying clean. Cameras need optical surfaces that do not quickly degrade. Mechanical parts need materials that hold shape and lubrication behavior within tolerable limits. Power systems need chemistry that remains controllable. Venus attacks those assumptions with heat, pressure, and corrosive conditions together. A surface rover there would not be a Mars rover wearing heavier armor. It would need a different technology family: high-temperature electronics, pressure-tolerant structures, acid-resistant surfaces, and mobility systems built for a world that punishes ordinary mechanisms. Research in these areas is real, and it matters. But promising technology is not the same as a ready operating environment for humans. The human scene becomes even harder. On Mars, a spacesuit is already a small life support system. It must provide pressure and oxygen. Here it must manage heat and communication. Mobility, dust, and radiation are part of the same burden. Yet the action remains recognizable. An astronaut could imagine walking to a rover, checking a cable, gathering a sample, and returning to an airlock. On Venus's surface, that familiar picture breaks. A suit would have to behave more like a compact pressure vessel and heat fortress. Every minute outside would be dominated by survival margins. Simple work would become hard before the science even began. Repairing equipment would mean sending one fragile machine, the suit, to fix another fragile machine in an environment hostile to both. A surface base would also struggle with logistics. Power systems would need to survive and stay serviceable. Landing systems would have to deliver mass into a dense atmosphere and onto a brutal destination. Communication, cooling, deployment, storage, and maintenance would all be shaped by the same hostile boundary. None of these problems is magic, but together they make the surface the wrong side of the argument. Mars asks humans to bring a livable bubble to a cold, thin world. Venus's surface asks for a livable bubble inside a hot, pressurized one. That is a worse starting point. The surface cannot be treated as a dramatic obstacle the story will later overcome. It is not a locked door with a better key waiting nearby. Here it is the wrong architecture for the question being asked. If the mission needs people and tools to function for long periods, the surface starts by making each task harder. Power systems, cooling loops, pressure vessels, and return hardware face the same penalty. Even the word landing changes. On Mars, landing is dangerous. But after touchdown, the vehicle has at least reached the environment where it is supposed to operate. On Venus, a surface landing would deliver the machine into the most punishing layer of the planet. Success would begin a countdown against heat, pressure, and material limits. That is not the kind of arrival that makes a human destination easier, so the title cannot mean that Venus is secretly welcoming on the ground. It cannot mean a surface colony is waiting behind one clever engineering trick. The surface is not the loophole, it is the warning label. The only reason the question survives is that Venus is not one environment from top to bottom. Its atmosphere is deep enough that altitude changes the planet dramatically. Pressure and temperature shift as height increases. Sunlight, wind, and chemistry shift with them. The surface remains lethal below, but the numbers above it do not stay the same. That vertical structure is the opening. It does not make Venus habitable. Here it does not erase the furnace under the clouds. What it does is move the serious comparison away from rock and into air. Mars offers the right kind of place in the wrong conditions. Land beneath a thin, cold, radiation-exposed sky. Venus offers the wrong kind of place at the surface, but possibly a different kind of destination above it, where some engineering problems change shape. Here is the critical turn. A crewed Venus mission, in the version worth discussing, would not try to use the ground as home. It would not use it as workshop or refuge either. Here it would have to stay high above it. The destination would be an altitude band, not a plane. A platform would have to remain within the layer that makes the mission possible. The condition is severe. Here the Venus surface would still be down there, but it would not be a backup. It would not be a place to land in an emergency. In practice, it would not be a second chance if the platform failed. Keeping the question alive means accepting that the mission has no friendly ground beneath it. Mars wins the ground. Venus gets one chance to compete only by refusing the ground entirely. That is why the next number matters so much. Roughly 50 kilometers above the surface, Venus stops behaving like the place most people imagine when they hear its name. High above Venus, the planet changes its numbers, not its nature, not its danger, its numbers. Around 30 miles, or roughly 50 kilometers above the surface, NASA describes a region where pressure can be similar to pressure at Earth's surface, and temperatures fall into a range of about 30 to 70 degrees Celsius. That is still hot. It is still inside an atmosphere no one can breathe. Here it is still embedded in a world with sulfuric acid clouds, strong winds, and a lethal surface below. But compared with the ground, it is a different mission problem. At the surface, Venus is a pressure cooker. Around 50 kilometers up, one of the hardest problems changes shape. A habitat no longer has to endure 93 atmospheres of outside pressure. The temperature is no longer hot enough to melt lead. Here the environment is not friendly, but it stops being impossible in the same way. Here is the loophole. The phrase Earth-like must be handled carefully here. It does not mean blue sky or open air. Here it does not mean forests, shirt sleeves, rainwater, or easy living. The phrase only means that two physical values, pressure and temperature, move into a range engineers can at least begin to discuss without starting from total impossibility. That narrow meaning is enough to matter. Pressure is one of the most basic facts of a habitat. On Mars, the outside air is extremely thin, so a habitat is a pressure vessel pushing outward. Every wall and hatch must hold internal pressure against an outside environment that provides very little. The same burden reaches the seals and windows. It reaches glove ports, airlocks, and cable pass-throughs too. A leak is a fight against near vacuum from a human point of view. In the Venus upper atmosphere, if the surrounding pressure is close to Earth's sea level pressure, the pressure difference can be smaller. That does not make the habitat simple. It still needs a controlled internal atmosphere with oxygen and filtration. Here it still needs thermal control and materials protection. Redundancy, power, and emergency systems remain part of the same burden, but one fundamental burden changes. A pressure vessel no longer has to be quite the same kind of pressure vessel. Temperature works the same way. 30 to 70 degrees Celsius is not a comfortable outdoor climate for humans. 70 degrees is dangerous heat. Even 30 degrees can be demanding depending on humidity, workload, equipment, and duration. A person would not be stepping out into the cloud air as if it were a warm afternoon. The habitat would remain the living place. Here the outside would still require protection. But the thermal fight is no longer against 467 degrees Celsius. It is no longer against the surface. That is the correction hidden inside the title. The comparison is not Mars' surface against Venus' surface. That contest is over. The comparison is Mars' surface against Venus altitude. A destination can be a height. That feels odd because exploration usually wants ground. Human maps love borders and coastlines. They love mountains, valleys, routes, and landing sites. A floating destination has no campsite in the usual sense, no road, no outcrop to revisit by walking, and no natural foundation under the habitat. But an atmosphere can still be a place in mission terms. Aircraft live in altitude bands. Balloons drift in pressure layers. Spacecraft use orbits which are not surfaces either. A Venus aerial platform would treat a layer of atmosphere as the destination. There is no terrain underfoot. The vehicle has to float and maneuver there, while still communicating, generating power, and supporting operations. It would not conquer Venus. Here, it would avoid most of Venus. The image matters. A habitat suspended above a world it cannot safely touch is not the same as a base on another planet. It would not be living on Venus in the way people imagine living on Mars. Here it would be living above Venus, inside a machine, in a band where the planet briefly becomes negotiable. The advantages begin to appear only after that move. Venus has gravity close to Earth's, unlike Mars. Venus is closer to the Sun, so solar energy is stronger before clouds, and engineering losses complicate the picture. A thick atmosphere may offer shielding that Mars's thin air does not. Pressure and temperature at altitude remove some of the absurdity of the surface. All of that begins only after the destination moves upward. The condition is severe. If a Mars habitat has problems, the crew is still on land. If a Venus platform has problems, the platform's altitude is part of survival. Staying in the right layer is not a convenience. It is life support. Too low, and heat and pressure increase. Too high, and pressure and temperature change again. Drift and buoyancy are not side issues. Station keeping, envelope health, atmospheric motion and power define the place. A mountain base can be damaged and still be a mountain base. Here, a floating base must keep being a floating base every second. That is where the apparent Venus win reveals its hidden cost. Pressure and temperature around 50 kilometers may be kinder than the surface, and in some ways kinder than a Mars habitat exposed to near vacuum. But the architecture must never forget what holds it there. The foundation is not rock, it is the envelope, the lifting gas, the control systems and the weather knowledge that keep the platform in the right layer. Materials and maintenance become part of the ground it does not have. Ballast, propulsion and power do as well. The crew would live inside an engineered exception. This distinction keeps the comparison honest. The upper atmosphere is not a hidden paradise. It is a narrow working layer that gives engineers better starting numbers while demanding a vehicle that behaves like both habitat and aircraft. A Mars base can be heavy in a way a floating Venus platform cannot. It can accept mass as protection, storage, or structure. In the clouds of Venus, every kilogram belongs to the flying system. It must be lifted, balanced, powered, and maintained. And that exception must deal with the Venus atmosphere as it really is, not as a soft cloud layer in a painting. The clouds contain sulfuric acid. Winds can be fast. Sunlight is filtered and scattered. External surfaces need protection. Sensors need windows or housings that survive. Solar arrays need placement and cleaning strategies. Docking systems need to work in a moving aerial environment. Repairs may have to happen with no ground, no open yard, and no simple way to step outside. So the loophole does not make Venus easy, it makes Venus discussable. That is a smaller claim, but a stronger one. A world with an impossible surface can still have a mission layer that changes the trade. Mars remains the solid destination with all the brutal problems of a cold, thin, low-gravity world. Venus becomes the suspended destination with gentler pressure and temperature in one band, but with no land beneath the crew and no surface refuge below. That abstract claim, that an aerial platform in the upper atmosphere could be a serious crewed destination, needed something more than physics to make it credible. It needed someone to sketch the engineering, what a vehicle would look like, how it would enter the atmosphere, how a crew would operate from it, and whether the numbers held when assembled into a real proposal. That is what a NASA study, published across 2014 and 2015, set out to do. A NASA acronym can make an idea sound more finished than it is. HAVOC stands for High Altitude Venus Operational Concept. The name is direct, almost blunt. It points to the same correction the Venus comparison needs. Not a rover crawling across the surface, not astronauts walking on hot rock, but a mission architecture built around altitude. HAVOC matters for that reason. It gives the upper atmosphere idea a serious anchor. The floating Venus picture is not only a science fiction poster or an internet argument against Mars. NASA Langley studied a concept in which Venus exploration happens from high in the atmosphere, where pressure and temperature are much more manageable than they are at the surface. But the careful word is concept. HAVOC was not an approved crewed mission. It was not a funded NASA plan to send people to cloud cities. It was not proof that humans can live above Venus. That detail is not a footnote. It was a proposed architecture, a study, and a way to ask what exploration might look like if the destination is the upper atmosphere instead of the ground. That distinction matters. Without HAVOC, the Venus airship idea can sound too airy, as if it belongs only to futurist illustrations. With HAVOC, it becomes clear that the physics was interesting enough for serious engineering attention. But if HAVOC is treated like a promise, the argument breaks in the other direction. A concept study can show that a question is worth asking. It cannot make the answer safe. The value of HAVOC is that it changes the starting line. A surface Venus mission begins with the planet's worst numbers. A high-altitude concept begins with a 50-kilometer loophole. It asks, if a crewed system can operate in that layer, what burdens are reduced and what new burdens appear? The right form of the question is narrower than the headline. It does not say Venus is better than Mars. It says the comparison depends on where the mission goes. In a high-altitude architecture, the vehicle is the base. An airship or aerial platform is not a delivery truck that lands somewhere and becomes less important. It remains the place of survival. Its envelope is not an accessory. The same is true of the structure and power system. Habitat controls, docking gear, and communications have to be part of the living world too. Emergency systems do as well. They are the world the crew inhabits. For engineers, this is a different kind of exploration. A habitat can be imagined as a building brought to a surface. A Venus platform at altitude has more in common with a ship or station that must continuously maintain its environment and position. The platform is not simply located in the atmosphere. In the working picture, it is negotiating with it. HAVOC's importance is that it takes this seriously enough to sketch mission phases and architecture around it. That alone separates it from Cloud City daydreaming. The study outlined a staged sequence. Robotic atmospheric exploration would come first. A crewed Venus flyby without entry would follow. Only after that would the concept move toward a 30-day crewed mission in the upper atmosphere using a solar-powered airship, and later toward a longer duration stay. Each phase would test the vehicle, the human factors, and the operational assumptions before the next phase committed to more. That structure matters. It means the concept was more than an airship sketch. It was a staged program that acknowledged how much would have to be learned before the hardest parts could be trusted. A real concept has to ask about entry. It has to ask about deployment. It has to ask how a large aerial vehicle becomes operational after arriving at Venus. At that point, the idea stops being a drawing and becomes a mission. It has to ask how crews reach it, live in it, work from it, and eventually leave. Each of those verbs hides difficulty. Arriving at Venus is not the same as arriving at a calm airport. A crewed mission would have to manage the transfer from Earth and the violence of atmospheric entry. Rendezvous and deployment would have to work. The vehicle would have to manage heat, structure, communications, and timing without treating any one of them as background. The platform cannot be treated as a magic balloon already waiting in the right cloud layer. It has to get there, open correctly, stabilize, and remain useful. Then it has to survive the place that makes it attractive. That is the recurring Venus pattern. The atmosphere helps by offering pressure, temperature, buoyancy, and possible shielding advantages. The atmosphere also charges a maintenance bill. Acid and wind have to be paid for, so do turbulence, material exposure, and altitude control. A concept study can frame that bill. It cannot pay it. At that altitude, this is where Mars still presses back. Mars missions have their own enormous unsolved burdens, especially for humans. But the surface operating model is easier to inherit from existing exploration. Landers land, rovers drive, instruments touch rock, habitats sit in place, power systems can be deployed across ground, cargo can wait. A failed wheel can remain a failed wheel rather than a threat to altitude. A Venus platform changes the failure logic. If the envelope is damaged, lift may be affected. If coatings degrade, the atmosphere touches the vehicle more aggressively. If power drops, station keeping or thermal control may suffer. If docking becomes difficult, resupply and rescue become harder. If the platform drifts into a less favorable layer, the outside conditions change around it. The mission is not only operating in an environment. For the crew, it is constantly remaining in the correct slice of that environment. HAVOC does not erase those problems. It makes them visible. In practice, that is a good thing. A serious concept is not valuable because it says yes. During the mission, it is valuable because it gives the question enough structure to stop being a slogan. It takes Venus might be easier and turns it into narrower comparisons. Pressure vessel design and gravity. The sentence stops being abstract there. It also asks about radiation shielding and solar power. It asks about atmospheric entry and aerial operations. It also asks about maintenance, abort modes, and return. Those categories are where the real answer lives. The upper atmosphere may soften some problems that Mars makes severe. Mars's low gravity remains a biological unknown. Mars's thin atmosphere gives little natural shielding. Mars is farther from the Sun with weaker solar input and dust complications. A Mars surface habitat must bring or build many layers of protection. Venus, at altitude, may offer better gravity and more surrounding atmosphere. It may also offer stronger sunlight and pressure conditions that reduce some structural burdens. But every one of those advantages depends on the platform working. Without a functioning aerial platform, the Venus advantage disappears. Without durable materials, the long mission disappears. The limit arrives early. Without safe deployment, there is no base. Rescue and return architecture are not optional because a crewed destination has to include a way home. Inspection, repair and maintenance in acid clouds and moving air are what turn the idea from a drawing into an operation. HAVOC belongs in the story as a doorway, not a verdict. It lets the comparison step through the surface boundary without pretending the surface has been solved. It shows why engineers could take high-altitude Venus seriously. At vehicle scale, this is where the comparison becomes physical. It also marks the line between disciplined imagination and overclaim. For engineers, there is a quiet honesty in that. The most useful Venus idea is not the loudest one. In the working picture, it is not a floating city glowing peacefully above yellow clouds. It is a carefully bounded mission concept asking whether a hostile planet has one layer where human exploration might trade impossible problems for merely extreme ones. That trade is worth studying. At that altitude, it is not the same as being ready. Once that is clear, the comparison can move from pictures to constraints. Mars has the ground. Venus has the altitude loophole. HAVOC shows that the loophole was serious enough to examine. The next question is what a human body would notice first if the platform actually worked. A cup floating inside a cabin does not know whether the world outside is red or yellow. It only knows the pull. If that cup is inside a habitat on Mars, it falls with about 38% of Earth's gravity. If it is inside a floating platform high above Venus, it falls under a pull much closer to the one human bodies evolved with. That sounds small at first, almost like background physics. It is not. Gravity is one of the few environmental facts that never turns off. Mars gives a crew a surface. It gives wheels something to grip, drills something to bite, landing pads somewhere to sit, and habitats a place to rest. But the body standing on that surface is still standing in partial gravity. Every step, every sleep cycle, every repair task, every month of blood circulation and bone loading happens at 0.38 g. No one has lived for years in Martian gravity. The moon showed that humans can move and work in low gravity for short missions. Space stations have shown how much the body changes when gravity nearly disappears. Mars sits between those worlds, and that middle ground is not well tested. That is the quiet uncertainty. Mars looks practical because the terrain is familiar. A boot print makes sense. A rover track makes sense. The quiet number becomes a working rule. A pressure dome bolted to the ground makes sense. But the person inside that dome is not living under Earth gravity. Bones respond to load. Muscles respond to load. Fluids in the body respond to where gravity pulls them. Balance, the heart, the blood vessels, and the way a person moves after sleeping all depend on a constant physical background that Mars cannot provide. Venus, strangely, can, not at the surface. The surface is still the wrong destination, hot enough to destroy ordinary machinery and buried under crushing pressure. But high in the atmosphere, where the air pressure and temperature become more familiar, the planet's gravity remains nearly Earth-like. A floating habitat would not give a crew land. It would not give them a valley, a hill, a cave, or a place to park a truck. It would give them weight. That may be one of the strongest real Venus advantages. It does not look like the usual frontier image. For the crew, it is just a body feeling something close to home every second. A wrench has familiar heft. A person climbing through a hatch uses muscles in a more familiar way. Fluids settle under a stronger pull. Exercise may still matter, confinement still matters, and medicine still has hard questions. But one of the biggest unknowns in a Mars settlement becomes less severe. The important word is may. Near-Earth gravity is valuable only if the place wrapped around the human body can keep existing. Gravity does not maintain an airship. It does not patch a leak, clean a solar array, resist acid droplets, or guarantee a safe return vehicle. A Venus platform could give the body a better load while making the machine around the body much harder to keep alive. In practice, that is the trade. Mars asks whether humans can stay healthy on land with weak gravity. Venus asks whether humans can use better gravity while living in a vehicle that can never stop flying. The Mars gravity question is genuinely unsettled. Space station data covers microgravity thoroughly. Lunar surface data covers about 2 weeks at 1/6 gravity. Mars, at 0.38 g, sits in a gap that no human has yet occupied for long enough to know what happens. Bedrest studies and centrifuge experiments can model partial gravity in limited ways, but they cannot substitute for years of actual exposure at that specific fraction of Earth's pull. Bone density loss, cardiovascular remodeling, fluid redistribution, and balance adaptation all happen on timescales that a crewed Mars mission would need to survive before anyone knows how severe the effects really are. A crew might arrive healthy, work productively for months, and only discover the depth of the physiological change when they try to return to Earth gravity. Venus removes that particular uncertainty almost entirely. A human body at 0.9 g is close enough to its evolutionary baseline that the adaptation problem changes category. The skeletal and cardiovascular loading question becomes less severe. Confinement, microbial exposure, radiation, and psychological strain remain Mars. But one of the larger biological unknowns in long-duration spaceflight simply does not apply. Neither question is small. The Mars problem is slow and biological. It may not announce itself in a single alarm. A crew can still walk and work. They can smile for a camera, collect samples, and maintain equipment, while deeper adaptation unfolds over months. Bone density and muscle strength may need countermeasures. Circulation, balance, and recovery may need them too. Some of those countermeasures may work well. Some may need artificial gravity, strict exercise, drugs, or mission limits. The hard part is that Mars gravity is not a known safe setting for long human lives. During the mission, it is a planet-sized experiment. Venus removes much of that specific uncertainty, but only by moving the entire base into the sky. A floating habitat at the right altitude could let the crew live under a pull their bodies understand better. It does not ask the skeleton to spend years adapting to a world that pulls less than half as hard as Earth. It does not make every falling object slow in the Martian way. Inside the habitat, the number becomes practical. It does not make every load, every step, and every injury recovery happen under a strange fraction of normal weight, but the condition is severe. The crew must remain in the right atmospheric layer, which means altitude control becomes a condition of life. The envelope has to stay intact. Propulsion, ballast, power, guidance, and docking cannot be treated as separate conveniences. Supplies still have to arrive, waste heat still has to leave, and medical emergencies still happen inside a floating station with no hospital below it. Mars can fail in many ways, but its failures keep meeting the ground. A broken rover stops where it is. Cargo waits where it landed. A habitat can be buried, shielded, expanded, and connected by cables. If a solar array needs work, the crew can at least imagine going outside onto a surface, however hostile, with tools and procedures. A Venus airship has no such resting state. Its safe place is an altitude, not a location. Too high, and the environment changes. Too low, and the world below becomes less forgiving with every kilometer. The platform is the ground, the platform is the shelter. That changes the job completely. The platform is the pressure system, the power plant, the dock, and the lifeboat staging area. That makes the gravity advantage real, but trapped inside another problem. Turning gravity into a scoreboard point is tempting. Venus, near Earth. Mars, 0.38. Venus wins, but missions do not work as scoreboards. A human body is only one part of the system. The question is whether the whole system becomes safer, simpler, or more survivable. In gravity alone, Venus has a powerful claim. It gives crews something Mars cannot give by building better habitats or driving better rovers. Mars cannot make itself pull harder. It can only compensate. Venus does not have to compensate for gravity. It has to compensate for almost everything else. For engineers, that is why this advantage is quiet. It does not make Venus friendly. It does not make the clouds a home. The comparison becomes hardware at that point. It simply points to one of the weaknesses hidden inside the Mars picture. A rocky surface can look like the natural human destination, while the body standing on it is still living in an experiment no human civilization has ever run for long. The Venus idea turns that inside out. The place with no ground may give the body a more familiar world. The constraint shows up before the plan gets far. The place with land may ask the body to accept a weaker one. And once the comparison shifts from what can be stood on to what can protect a human body over time, another invisible hazard comes forward. A thin wall of habitat metal is a small thing to place between a human body and deep space. On Earth, that thin wall is not alone. Above it sits an atmosphere, kilometers and kilometers of air, taking the first blow from particles and radiation that would otherwise reach the ground more easily. Earth's magnetic field helps too, but the atmosphere is not decoration. It is mass overhead. It is shielding made from sky. Mars does not have much of that. A person standing on Mars is still under a sky, but it is a thin one. The air is mostly carbon dioxide, cold and dusty and weak by Earth standards. It can move dust, it can make weather. In the working picture, this is where the comparison becomes physical. It can color the horizon. But as radiation protection, it leaves a great deal of work for the habitat and the suit. Mission design and shielding materials have to carry the rest. Radiation is not a single simple danger. Solar energetic particles can arrive from the sun. Galactic cosmic rays arrive from beyond the solar system and are hard to block completely. Long missions bring long exposures. The problem is not solved by bravery, by calling Mars a frontier, or by putting a flag on the map. That design burden stays with the crew. At that altitude, this is where Venus starts to look strange again. The same planet that is impossible at the surface carries an enormous atmosphere above it. At the right altitude, a floating platform would not sit in empty space or under a thin Martian sky. It would sit inside a thick column of atmosphere with much more mass around it and above parts of it than Mars can offer at the surface. That does not make Venus safe. It does make the shielding question different. A Mars habitat must bring shielding into a world that does not provide much atmospheric protection. It may use regolith and water. Food stores, buried modules and storm shelters can become part of the shield. Those ideas are serious. Mars has soil everywhere, and that soil can be useful if machines can move it, pile it, and build with it. But the crew must land into a place where radiation remains one of the major environmental risks. The shield has to be part of the architecture. A Venus platform may be able to borrow part of its shield from the planet itself. For the crew, that is the apparent win. The air is more than something outside the habitat. It becomes a layer of protection. A crew floating deep enough in the Venusian atmosphere may receive less radiation than a crew on the Martian surface, because the atmosphere above and around the platform has more stopping power than Mars's thin air. The relevant measurement is dose equivalent over mission duration. A crewed Mars surface mission of several hundred days would accumulate radiation from 3 sources: the transit out, the surface stay, and the transit back. The surface stay benefits from the planet's bulk blocking radiation from below, but the thin atmosphere provides limited overhead shielding. Mars Science Laboratory's radiation detector measured real doses during transit and surface operations, giving mission planners concrete numbers to design around. For a Venus aerial platform at the right altitude, the atmospheric column above and around the vehicle represents more shielding mass than the Martian sky can offer, though the geometry depends on the direction the radiation is arriving from. For galactic cosmic rays arriving from all directions, a thicker surrounding atmosphere may provide measurable reduction in dose. Solar energetic particle events require dedicated storm shelters, regardless of which planet the crew is near. The Venus shielding advantage in this category is plausible but conditional, and the conditions involve altitude bands that have not yet been measured for radiation dose the way Mars has. The condition is altitude, too high and the protection changes, too low and the temperature and pressure begin moving toward the nightmare below. The platform has to live in a band where many demands meet at once. Pressure and temperature matter, chemistry and wind matter. So do communications, power, buoyancy and radiation. That band is not a meadow. In practice, it is a moving engineering compromise. Even within that band, radiation does not disappear. Solar storms still matter. Habitat design still matters. Mission duration still matters. The direction and thickness of shielding still matter. A sleeping area may need more protection than a work area. A storm shelter may still be needed. The crew may need procedures for unusual solar events. The atmosphere helps, but help is not the same as rescue. During the mission, there is also a cost hidden inside the shield. Venus's atmosphere is not a clean blanket. Sulfuric chemistry makes the air hostile. Cloud droplets carry sulfuric acid. Fast winds can move through the layer. A quiet number becomes a working rule. The environment that may reduce one invisible hazard introduces material hazards across the outside of the vehicle. Windows, seals, sensors and antennas all sit in it. So do solar panels, joints, valves, coatings, and the outer skin of the platform itself. For engineers, that is the Venus pattern in its purest form. The thing that helps is also the thing that attacks. Mars has dust and cold. It has abrasion and perchlorate chemistry to respect, but a parked machine can remain a parked machine. A rover can wait. A habitat wall can be covered. A small difference on paper becomes a daily condition. A solar array can be cleared or replaced on a surface. The protective strategy can become part of a growing base. On Venus, the atmosphere is active architecture. It holds the platform up. It may shield the crew. It also surrounds the platform at all times. In the working picture, there is no stepping away from it. No clean vacuum waits outside, and no friendly air waits there. Every external repair happens in the same medium that causes the problem. This makes the phrase, living inside the shield, both promising and unsettling. The crew is not hiding under a pile of rock. They are suspended in the very material that gives the mission its advantage. If the atmosphere reduces radiation exposure, that is a real point in Venus's favor. But the platform must survive contact with that atmosphere for the full mission. Its materials must tolerate acid exposure. Its systems must handle winds and altitude control. Its maintenance plan must assume the outside world is never neutral. Mars has the opposite shape. The outside world is not gentle, but it is a place with ground. Radiation shielding can be heavy, ugly, and hard to build, yet it can be placed, buried, rearranged, and inspected. A base can accumulate protection. The first missions may be sparse, but the logic of improvement is clear. Land more equipment, move more mass, build thicker shelters, cover sensitive spaces. A Venus platform cannot pile the atmosphere into walls. It can only sit inside it and design around it. The shield is everywhere, but it is not a stack of blocks a crew can move by hand. It cannot be made thicker in one direction without changing the vehicle or the altitude. At that altitude, it is a gift from the planet, and the mission must accept the terms. For the crew, that is why radiation cannot be used as a simple Venus victory. In practice, it is better to say the upper atmosphere may offer a shielding advantage. During the mission, that is cautious, but it is also more interesting. It means Venus changes the radiation problem from how much shielding must be carried or built on a thin-aired world to can a crew safely operate inside a thick, corrosive, and moving atmosphere that provides some of the shielding for them. Those are not the same mission. One asks a base to make its own protection. The other asks a vehicle to survive inside protection that is never passive. Mars exposes the crew more and gives them ground to work with. Venus may protect the crew more and takes the ground away. The advantage is real only if the platform can remain healthy, and keeping it healthy demands a power supply that never stops. Another apparent Venus win enters there with the same pattern, advantage followed immediately by condition appearing again. A solar panel in sunlight looks like one of the cleanest machines humans know. No flame, no smoke. The appeal is easy to understand. No moving piston, just a dark surface catching light and turning part of it into electricity. That image is already familiar. Landers and rovers unfolding panels, dust settling over them, engineers watching power margins from far away. On Venus, the first thought is even simpler. Venus is closer to the sun. More light should mean easier power. At the level of raw sunlight, Venus has the advantage. Venus orbits inside Earth's path around the Sun. Mars orbits farther out, around 1.5 times Earth's distance. Sunlight weakens with distance. Mars starts with less solar energy before dust storms enter the calculation, before seasons matter, and before engineers choose latitude or panel angle. Venus starts with more. That is a real physical difference. It should not be waved away. A floating platform high in the Venus atmosphere could, in principle, benefit from stronger sunlight than a similar system near Mars. Power matters for every living system on the platform. Life support needs it, communications need it. Pumps and fans draw from the same electrical budget. So do heaters, coolers, and computers. Science instruments, propulsion and altitude control draw from it too. A mission that needs electricity would rather not begin under weak sunlight if it has another option. Mars has already shown how dust can complicate solar power. Dust can settle on panels. Dust storms can dim the sky. Even when nuclear power is used, solar energy remains a major part of how people imagine building up surface infrastructure. Venus seems to offer the opposite problem, too much nearby sun to waste. But useful power is not the same as sunlight in an orbital diagram. A panel has to be placed somewhere and face the right direction often enough. The air around it has to be survivable for the hardware. It must stay clean, cool, wired and repairable enough to be trusted. The electricity has to be stored for night-side operations or cloudy intervals. The platform has to keep generating power while it drifts, turns, rides winds, and possibly moves between different lighting conditions. A Mars base can spread arrays across the ground. It can anchor them. It can wire them to buried cables. The claim has to pass through machines, not slogans. It can send a rover to inspect them. It can brush or shake panels. It can tilt them, replace them, or abandon them. If one field performs badly, another can be laid out somewhere else. The surface gives power systems room. A Venus platform has stronger sunlight, but far less patience in the architecture. The power system is part of a flying machine. Panels may sit on the top of an airship, along a truss, on deployable wings, or on separate floating units. Every square meter added to collect power changes the vehicle. Mass changes, drag changes, balance, structural load, and maintenance exposure change with it. The arrays are not lying in a quiet field. They are attached to the thing keeping the crew alive. Then come the clouds. Venus is bright from the outside because its clouds reflect so much sunlight. That brightness seen from space does not mean every useful altitude receives simple, direct, and steady light. Clouds scatter and absorb. The platform's position in or near cloud layers matters. Above some cloud decks, sunlight may be strong. Within them, the light field becomes more complicated. Below them, less useful sunlight may reach the vehicle. The question becomes not, how close is Venus to the Sun, but where exactly can the power hardware live? If arrays must be placed high for better light, they may need extra structure. Cabling, pointing, and maintenance access can complicate the platform. If they sit where the habitat sits, they must tolerate the local cloud chemistry. If they are exposed to sulfuric acid aerosols, the fragile parts must keep working. Coatings and seals become survival hardware. So do clear surfaces, hinges, and electrical connections. If they are shielded too heavily from the environment, they may collect less light or gain mass. Mars makes power hard with distance, dust, and cold. Venus makes power hard with placement, chemistry, motion, and access. That difference matters because maintenance is not a small footnote in long missions. A solar array is not useful because it works on the first day. It is useful because it keeps working after thermal cycles, mechanical loads, contamination, and repairs. On Earth, solar farms have roads and trucks. They have technicians, replacement parts, weather forecasts, and supply chains. A crew on Mars would at least have a surface on which to build a harsh and limited version of that logic. On Venus, the repair yard flies. A panel cannot simply be dragged into a workshop unless the platform has been designed around that operation. A failed hinge outside the habitat may require robotics, suits, sealed maintenance ports, or replaceable modules. The mission cannot postpone that limit. A damaged surface may be chemically contaminated. A loose component is not lying on the ground waiting to be retrieved. It may be gone into the clouds below. Stronger sunlight is valuable, but it is not free. For engineers, there is also heat. More sunlight means more energy arriving, and not all of it becomes electricity. Some becomes waste heat. In a floating habitat, heat has to be managed carefully. The platform must keep people, electronics, batteries, and structural materials inside acceptable limits while sitting in a warm environment. Power generation and thermal control become linked. A design that collects more light may also need better ways to reject unwanted heat. Mars has the opposite trouble. In the working picture, it is cold. It receives weaker sunlight. It needs heat and power in a thin atmosphere that does not carry heat well. Dust events make that difficult, but cold and weak sunlight are problems engineers know how to frame. They can use insulation and heaters. They can also use nuclear sources, batteries, fuel cells, and surface arrays. Venus asks for a different kind of confidence. The platform must produce power in a cloudy, acidic, and moving atmosphere while remaining light enough and stable enough to fly. Redundancy becomes harder when every backup adds mass. Maintenance becomes harder when every external surface sits in a hostile medium. Storage becomes critical when generation changes with position, cloud, day-night cycles, or operational needs. At that altitude, this is why orbital distance should not become a scoreboard. Venus receives more sunlight than Mars. For the crew, that is true. It may give a floating mission a serious power advantage. In practice, that is also plausible. But the mission does not receive power from a textbook diagram. It receives power through hardware that has to be bolted, stretched, sealed, and coated. Then it has to be cleaned, cooled, and repaired in a real environment. Mars's weaker sunlight comes with the great advantage Mars keeps returning to: ground. Power systems can sprawl. They can be modular. They can be serviced from a base that does not have to stay aloft. Dust is a serious enemy, but it is an enemy on a surface. A dusty panel is still somewhere. Venus's stronger sunlight comes with the question of what the platform can carry and maintain. That question brings the architecture into focus, because the power problem and the maintenance problem and the structural problem all meet in the same place: the vehicle. And the vehicle is worth looking at directly. An airship hanging over Venus is one of those images that feels wrong until the physics starts to help. Below it, hidden by cloud, is a surface no human machine can casually use: crushing pressure and furnace heat, and a terrain that punishes ordinary electronics and structures. Around it, at the right height, the air is dense enough to matter. The platform is not trying to sit on the ground, it is using the atmosphere as part of the machine. That is the beautiful idea. Venus's atmosphere is mostly carbon dioxide, far denser than the air around Mars. In a thick carbon dioxide atmosphere, lighter gases can provide buoyancy. Even ordinary breathable air, in simplified descriptions, can act as a lifting gas because it is lighter than the surrounding carbon dioxide mixture. That makes the concept feel almost magical. The same air a crew needs inside a habitat might also help lift it. The idea should not be made too cute. A real system would need structure and envelope materials. It would need ballast and gas management. Power, propulsion, and thermal control would have to work with docking systems, emergency systems, and many layers of redundancy. But the physical hook is real. The Venus atmosphere at 50 kilometers is roughly 60% as dense as Earth's atmosphere at sea level. An airship filled with a gas lighter than the surrounding carbon dioxide mixture does not have to work as hard to float as a similar vehicle would in the thin air above Mars, where there is almost no atmosphere to displace. During the mission, this is not a trick. Basic atmospheric physics applies to a planet that happens to have exactly the wrong surface and exactly the right altitude layer for this kind of architecture. The same density that crushes ordinary machinery at the ground provides genuine lift at height. A floating platform on Venus is more than fantasy pasted onto a hostile planet. It comes from an actual difference between environments. Mars offers land but almost no air to float in. Venus offers no usable surface but an atmosphere thick enough to support an aerial architecture. Each planet gives the mission something and withholds something else. At the right Venus altitude, another advantage appears. The pressure outside can be closer to Earth-like values than the near-vacuum conditions a Mars habitat must resist. A Mars base is a pressure vessel sitting in a thin atmosphere. Inside, people need breathable pressure. Outside, there is very little pressure pushing back. Every boundary must respect that difference. A wall or seam cannot be treated as ordinary structure. Neither can a window, hatch, cable pass-through, or airlock. A Venus platform at the right height may have a smaller pressure difference between inside and outside. That does not make the habitat simple. The outside air is not breathable. For engineers, it is hot or warm depending on altitude, chemically aggressive and moving. But the pressure vessel problem may be less extreme than placing a human cabin on Mars. In the working picture, This is why the airship concept has such pull. It seems to turn Venus's biggest feature into an ally. The thick atmosphere becomes lift, the pressure becomes less alien at altitude. The planet's gravity becomes almost familiar. Sunlight is stronger than at Mars. Radiation may be softened by atmospheric mass. For a few moments, the whole comparison feels as if it has flipped. Mars has the obvious surface, Venus has the stranger architecture. The danger is stopping there. Many Cloud City dreams stop at the first elegant sentence. Breathable air floats in carbon dioxide. But buoyancy is not a mission. Buoyancy is one force in a system that must operate for days, months, or longer. The platform still has to hold altitude and pressure. It also has to hold chemistry, power, and structural health together. An airship is not a house that happens to float. The platform is an aircraft that must never be allowed to forget it is an aircraft. Its envelope is not decoration. At that altitude, it is the difference between staying in the temperate layer and descending toward conditions that become more destructive with depth. Its gas cells and valves are life support structure, so are pumps, seams, and coatings. A Mars habitat can be ugly and heavy. For the crew, that is one of Mars's advantages. A pressure vessel can be landed and covered. It can be braced, expanded, and connected to other modules. If it is too massive, the launch system pays the price. If it is difficult to move, it can stay still. Mars allows stillness. A Venus platform does not. Mass is more than expensive to deliver. It changes the flying system. Add shielding, and the platform must lift it. Add batteries and spare parts, and the lifting system must carry them too. Add robots, docking hardware, or emergency vehicles, and the same burden grows again. Add stronger materials to survive the environment, and the structure gains weight. Add more lift, and the envelope grows. A larger envelope sees more wind load, more surface area, more maintenance, and more exposure. The beautiful idea starts to unfold into a long chain of consequences. In practice, there is leakage. Every airship must manage gas. On Earth, leakage is an operational issue. On Venus, it is tied to altitude, safety, and survival. Lifting gas lost into the atmosphere may be difficult to replace. Breathable air used as lift sounds elegant, but breathable air is also the crew's atmosphere. The system would need careful separation, storage, monitoring, and emergency planning. During the mission, there is material lifetime. The platform's outer surfaces face sulfuric acid droplets in the cloud environment. Coatings can protect, but coatings age. Seals can resist, but seals fail. Transparent surfaces and sensor windows have to keep their function while exposed. So do solar arrays, antenna housings, external joints, and docking interfaces. The airship is more than floating in air. The platform is floating in an atmosphere that wants to become a slow maintenance bill. For engineers, there is wind. Venus's atmosphere moves powerfully. A floating platform may ride with the winds, use them or fight them depending on the mission plan. But winds affect communication geometry and station keeping. They also affect navigation, docking, and emergency return. If the platform needs to stay near a certain latitude, altitude, or relay path, motion becomes more than scenery. It becomes a constraint. In the working picture, there is repair. A Mars base can send a suited crew member or robot across ground, with all the difficulty that implies. It can still think in terms of walking, driving, carrying, and placing. A Venus platform must repair itself while suspended. External work may require robotic arms, sealed suits, maintenance tunnels, or replaceable panels and systems designed never to need human hands outside. Every one of those options adds mass and complexity. Then comes docking. Cargo must arrive somehow. Crew must arrive and leave. A floating platform has to meet vehicles in a moving atmosphere. The dock must be strong, sealed, tolerant of motion, and protected from the same environment as the rest of the structure. A bad docking event is more than a dent in a harbor. It may threaten the vehicle that is acting as the base. At that altitude, there is evacuation. For the crew, this is the question hidden beneath the elegance. If a Mars habitat has a major problem, The crew may have nearby rovers and other modules. They may have cached supplies and at least a surface architecture designed around fallback points. None of that is easy, but it can be imagined as infrastructure on land. If a Venus platform has a major problem, the fallback is another flying system, or it is a docked ascent vehicle, a nearby platform, or a procedure that has to work in the air. In practice, there is no valley to walk into, no cave to shelter in, and no cargo cache sitting on the ground. The ground is not a refuge. During the mission, it is the thing the platform has to stay above. This does not make the airship idea foolish, it makes it honest. And honesty means asking what the platform actually has to survive, not on a diagram, but over weeks and months in the real atmosphere. A maintenance hatch opens into yellow-white cloud, not onto gravel, not onto a pad poured beside a habitat. This is where the comparison becomes physical, not onto a cold plain where a tool cart can wait under a dust cover. Outside the hatch is moving air, acid mist, sunlight scattered through cloud, and the long, invisible drop toward a surface no crew can use as a fallback. That is where the elegant Venus idea starts to change shape. A floating platform solves one terrible problem by refusing to land. It avoids the furnace ground. It avoids the crushing pressure below. The quiet number becomes a working rule. It lives in the layer where temperature and pressure can stop looking impossible. The apparent win is real enough to matter. If the destination is placed high in the atmosphere, Venus suddenly gives an engineer something to work with, but the condition is just as real. The destination is not a place. The machine is staying inside a narrow operating layer. It has to keep altitude and hold its shape. The crew would live with that difference, not merely calculate it. It has to protect its skin and make power. It has to exchange heat, communicate and handle docking while the surrounding world touches every outside surface. Repairs belong inside that same problem. The environment on Mars is hostile, but the floor stays where it is. On Venus, the floor is part of the problem. The clouds are more than color, they are chemistry. Venus's cloud deck contains sulfuric acid droplets, and those droplets turn the outside of a floating outpost into a materials test that never ends. Every exposed surface has to be chosen with that cloud chemistry in mind. The envelope that holds lifting gas faces it first. Protective coatings, seams, hatch seals, valve seals and sensor windows face it too. Solar arrays, antenna covers, docking hardware and moving parts all have small exposed edges where real machines begin to fail. This does not mean acid instantly eats everything. That would be too simple and too dramatic. The harder truth is quieter. The atmosphere becomes part of the maintenance schedule. A panel that works on Earth may need a different coating. A seal that survives in a clean test chamber may behave differently after long exposure to aerosols. The maintenance problem is not a footnote. A sensor window may need to keep seeing after weeks or months of contamination. A solar array may need to keep its surface useful while suspended in a chemical fog. For engineers, that is the bill attached to the Venus win. The planet offers a layer where pressure and temperature look surprisingly familiar. Then it wraps that layer in acid-bearing cloud and wind. Wind matters because a floating platform is not a building. In the working picture, it is not bolted to bedrock. Venus's upper atmosphere can move fast, and even when a craft rides the flow rather than fights it, motion becomes operational. Position matters, altitude matters, sun angle matters, communication geometry matters. If the platform drifts away from an intended region, that may affect power and navigation. It may also affect rendezvous, thermal control, and safety margins. A small drift on a surface base can be nothing at all. A rover parked a few meters from its target can drive back. Language meets equipment there. A habitat on Mars does not slide down into denser and hotter air because a control system falls behind. A Venus platform lives by staying in the right layer. That makes altitude control feel less like steering and more like life support. Too high, and the temperature may change. so may the pressure, winds, and power conditions. Too low, and the platform begins moving toward a world where pressure and heat rapidly become less forgiving. The exact danger depends on the architecture, but the basic shape is clear. Losing altitude is not like rolling downhill into a valley. The vehicle is moving into a deeper part of the atmosphere that the whole mission was designed to avoid. At that altitude, this is why the airship idea cannot stop at buoyancy. Buoyancy makes the concept beautiful. Maintenance makes it serious. A floating habitat needs an envelope, and an envelope is not a magic word for thing that stays inflated. It is a large exposed structure. It has to survive bending and loading. It has to survive temperature changes and gas handling. It has to survive small leaks, material aging, acid exposure, and repeated inspection. If the platform has compartments and valves, they are not background details. Pumps, ducts, and lifting gas systems are not background details either. They become the hidden plumbing of survival. On a calm diagram, the outpost hangs in the cloud layer like a simple object. In operation, it is a whole set of surfaces and pressures trying to remain inside tolerances. The comparison with Mars becomes less flattering to Venus here because Mars can use stillness. A Mars base can accumulate mass. It can place spare tanks beside a wall. It can bury cables. That limit reaches the crew before anything dramatic happens. It can park a robot near a broken panel. It can stack replacement parts in a storage bay and send a suited crew member outside to drag one into place. None of that is easy in the cold, thin Martian air. Dust gets into mechanisms. Radiation is a burden. The atmosphere is too thin to breathe and too thin to shield well, but the ground gives operations a grammar humans already understand. Stop, anchor, dig, park, cache, return. A Venus platform has a different grammar: float, hold, seal, balance, dock, climb, avoid descent. That difference reaches into every repair. A loose tool on Mars falls to the ground. A loose tool outside an aerial platform may be gone. For the crew, this is where the comparison becomes physical. A replacement panel on Mars can rest on a stand. A replacement panel on Venus has to be handled in a moving atmosphere around a vehicle that must keep flying. The quiet number becomes a working rule. A broken external mechanism on Mars may be ugly, cold, dusty, and dangerous to reach. A broken external mechanism on Venus may be all of that, plus coated in acid droplets and attached to an altitude-dependent vehicle and exposed to winds that do not care about the repair plan. In practice, this is where easier starts to split apart. Venus may make the pressure vessel easier in one sense. At the right altitude, the outside pressure can be closer to Earth's surface pressure than the near vacuum around a Mars habitat. That reduces one kind of stress. It may make some structural problems less extreme. But Venus then adds other stresses. The outer structure is not sitting in emptiness. During the mission, it is sitting in an atmosphere that pushes and moves. It carries droplets, changes with altitude, and demands constant protective design. A Mars habitat must keep air from leaking into a thin outside world. A Venus platform must do that while also remaining buoyant, chemically protected, aerodynamically stable, and operationally reachable. The apparent Venus win is pressure. The condition is altitude. That detail reaches the schedule, the tools, and the risk board. The hidden cost is that the altitude has to be maintained by a machine whose outer skin is also its survival system. That cost includes docking. A surface base can make a landing zone, improve it across missions, and treat it as fixed infrastructure. A floating platform has to negotiate its dock with a moving vehicle in a moving sky every time a resupply or crew transfer is attempted. The dock is not a permanent structure. Another system must function without ground beneath it, all of which brings the comparison back to the same conclusion. Venus's pressure advantage is real in one layer. The work required to stay in that layer is also real. So is the work of protecting everything the atmosphere touches, and keeping the platform capable of docking, repair, and departure. The bill is not paid at launch. It accumulates every hour the platform floats in a sky that is never neutral. Mars has its own running bill, dust and cold, radiation and low gravity, and a surface that demands constant work just to stay functional. But the surface gives maintenance somewhere to happen. On Venus, the place where the work needs to happen is the same place that makes the work harder. A rover track on Mars is a small thing, just a pressed line in dust, but it tells a story Venus cannot tell from its clouds. A machine touched the ground and rolled forward. It stopped, turned, looked around, and kept working. Then it did it again, day after day, season after season, across a real surface that stayed under its wheels. That is not romantic, it is operational. Mars wins the first picture because it gives exploration a flaw. Even after the Venus altitude loophole is understood, that advantage does not disappear. It becomes more important because the comparison has finally become fair. Venus may offer a strange upper air layer where pressure and temperature start to look useful. Gravity, sunlight, and atmospheric shielding start to matter there too. But Mars offers something simpler and older. Land that can be used as land. A surface is more than a place to stand. For engineers, it is a working medium. Machines can park, they can wait, they can anchor equipment into the ground, they can drill, they can scoop, they can cache samples, they can return to a rock outcrop after a long detour. They can photograph the same hill at different times of day. They can build a map where every feature has a location that does not float away. That matters for science. It also matters for survival. A Mars base could build slowly. A landing pad could become more than a bare patch of ground. Power systems could be spread out and serviced. Habitats could be connected. Spares could be stored in known places. Robots could drive between them. Cables and berms could stay. Trenches, shields, shelters, and storage zones could accumulate into something like an outpost. None of this makes Mars easy. It only makes Mars legible. The land gives operations a pattern that human exploration already understands. A camp may slowly become a station, and a station may grow into a network. Over time, that network starts to behave like infrastructure. Each mission can leave behind useful mass in a known location, and the next mission can build from it. A floating Venus platform has to keep flying. It may grow, dock, receive cargo, and receive service, but it does not have the same relationship with its environment. It cannot pour a foundation into the cloud deck. The missing surface keeps returning. It cannot bury a shelter under atmospheric soil. It cannot store a broken component behind a rock and leave it there until a robot arrives. Mars's advantage is not that it is gentle. Mars is cold. Its air is too thin for unprotected lungs and too thin to give much shielding. Its dust is invasive. Its sunlight is weaker than Earth's, and long dust events can make power planning difficult. Its gravity is only about 0.38 g, and nobody has yet proved that human bodies can thrive for years in that field. Radiation remains a serious design burden. A Mars habitat is still a closed machine in a hostile world, but when something heavy has to be moved, Mars lets it rest. That sounds almost too basic to count, until the comparison is a floating platform above Venus. A surface lets engineers cheat in ordinary ways. Broken panels can be laid flat, and storage can sit beside a habitat. Rovers tow trailers. Robot arms brace against the ground. Drilling rigs push downward because the planet pushes back, and shelters can borrow regolith as shielding. A route can be driven again because the ground is still there. A Venus airship may have elegant buoyancy, but it does not have that kind of reaction surface. Every external repair is part aircraft maintenance, part chemical protection, and part altitude management. The platform cannot simply become heavier and heavier without consequence. Mass is more than stored. It is lifted, balanced, and carried. Mars also wins on direct access to geology. That may sound like a science-only point, but it reaches into human presence. Rocks are records. Ice deposits are resources. Regolith is shielding material, construction material, hazard and evidence all at once. Mars lets instruments touch the surface that holds the planet's history. It lets drills search for buried ice or old environments. It lets sample tubes, caches and traverse plans build a record over time. Venus's clouds can be studied from within. Its atmosphere is scientifically rich. Its chemistry, winds and deep greenhouse state matter enormously. But a floating platform is separated from the surface by the very conditions that make the surface unreachable. The rocks below are not a place to work. They are a remote target under a crushing, superheated atmosphere. In the working picture, that is one reason Mars has become the world of rovers. The machines have not made Mars friendly. They have made Mars familiar. They have shown that wheels can cross its terrain and cameras can choose targets. Drills and scoops can work. Robotic arms can place instruments. Long surface missions can survive far beyond their first expected timelines. This heritage matters. Experience is not proof that humans can live there, but it is proof that Mars' surface operations are not only imagined on paper. The planet has been worked by machines. Its dust and rocks have been met directly, so have its slopes, seasons and power cycles. Engineers have learned from broken wheels and dust-covered panels. They have learned from landing hazards, communication delays, and unexpected terrain. Mars has a history of operational scars. The twin rovers Spirit and Opportunity were designed to last 90 days. Opportunity continued for nearly 15 years. Curiosity crossed terrain types the engineers had never encountered in testing and adapted. Perseverance conducted a small but real demonstration of propellant production from the Martian atmosphere, a technology that will directly inform the design of return vehicle fuel systems for any crewed mission. Those lessons are cumulative. A crewed Mars mission would not be starting from assumptions. It would be inheriting a body of knowledge built by machines that actually operated in the place the crew intends to go. That inheritance changes what the first human mission has to figure out alone. Venus's upper atmosphere has serious mission concepts, but not the same record of long-lived, complex, human-scale operations. The aerial idea is plausible because the physics gives it an opening. Mars is plausible because the ground has already hosted years of robotic work. Those are different kinds of credibility. Mars also has a clearer infrastructure path for emergencies, even though every emergency there would still be frightening. A habitat leak or rover failure can become life-threatening, so can a power problem, a medical event, a dust storm, or a radiation warning. But the crew's assets can be distributed across a surface. Redundant habitats can be separated by distance. Power units can be placed in different locations. Supplies can be cached. Rovers can make rescue routes. Navigation can use landmarks. A damaged vehicle can stop moving without falling. The surface lets failure become local. On a Venus platform, failure more easily becomes systemic. An envelope problem affects lift. A lift problem affects altitude. An altitude problem affects temperature, pressure, and survival margin. A docking problem affects resupply and escape. A corrosion problem may affect multiple exposed systems at once. The vehicle and the habitat are deeply entangled. A Mars habitat is also entangled in its own way. Power is life support. Dust can affect solar generation, but the ground allows separation. Parts of the base can be spread out. Some failures can be isolated by distance, walls, berms, or backup vehicles. The work is not glamorous. At that altitude, it is one of the main reasons land is useful. Mars earns those operational advantages, but getting there in the first place is its own argument. And proximity, the number that seems to settle the question before any engineering begins, turns out to carry less weight than the orbital diagram suggests. Venus can be the nearer planet and still not be the simpler trip. That sounds wrong at first because distance feels like the cleanest number in spaceflight. Less distance should mean less trouble. A shorter gap should mean a safer mission. The inner neighbor should be easier to reach than the cold red world farther from the sun. Sometimes Venus is closer to Earth than Mars is. Its orbit lies inside Earth's orbit, while Mars circles farther out. In the simplest mental picture, Venus seems to win before any engineering begins. But planets are not train stations. They move, Earth moves. Launch windows open and close. A spacecraft does not point at where a planet is and drive straight across the gap. It follows an orbit around the Sun, timed so that the departing world, the spacecraft, and the destination arrive at the right places together. The useful question is not which planet can be nearest in a snapshot. It is what kind of mission that geometry allows. That is where closer starts to fray. An easier mission needs more than a small minimum distance. It needs a departure opportunity. It needs a transfer time that a crew and vehicle can survive. The phrase becomes an engineering problem. It needs arrival conditions the spacecraft can handle. It needs a way to enter the destination environment and reach the working site. The boundary is operational from the start. It needs a stay that can last for a defined time, followed by a departure and a return to Earth that do not depend on a chain of miracles. A crew has to cross interplanetary space and arrive at Mars. The vehicle then has to land through air that is thick enough to heat it, but too thin to slow it easily. After the surface stay, the crew still has to launch back up. Mars return means ascent from a planet. Even at lower gravity than Earth, that is a major demand. Propellant, launch timing, rendezvous, surface systems, and long mission duration all become part of the architecture. Mars is not hard because it is farther. For the crew it is hard because the whole mission has to become a closed transportation system across years. Venus shifts the difficulty. The apparent win is that Venus can be attractive in travel geometry discussions. As Earth's inner neighbor, it can offer favorable opportunities that make engineers look twice. Some mission concepts have treated Venus as reachable in ways that may compare well against Mars in certain transfer or cadence assumptions. But the condition is architecture. Where exactly is the crew going? Not the surface. That has already failed the comparison. The destination is an aerial platform in the upper atmosphere, so arrival is more than arrival at Venus. In practice, it is arrival at Venus, atmospheric entry and deployment or rendezvous with a floating system. It also requires controlled transition into the right layer and safe connection to a platform that must already be stable or must be established during the mission. During the mission, that is not the same as landing on a pad. The planet being closer does not remove the need to meet the right moving target in the right moving atmosphere. A Mars landing site is fixed to the planet. It rotates and has weather. Dust, terrain hazards and lighting constraints matter, but it is still a place on the ground. If a base exists there, its coordinates remain its coordinates. Cargo can be sent ahead. Hazards can be mapped. Landing zones can be improved in principle. The surface gives mission planners a target that can accumulate history. A Venus platform is not fixed in that way. It may ride winds around the planet while controlling altitude and position within limits. In some designs, drift is not a failure but part of the operating plan. Any arriving crew or cargo has to deal with an atmospheric object, not a runway on rock. That does not make the problem unsolvable. It makes the word nearer incomplete. Arrival speed also matters. A spacecraft reaching Venus is falling inward toward the Sun. It must manage the energy of arrival. The thick atmosphere may help with braking, but using an atmosphere safely is its own discipline. Heat and loads matter. Navigation and deployment become part of the price. A dense atmosphere is not automatically a soft cushion. It can be a tool, but tools have operating limits. Mars has its own entry problem because its atmosphere is awkwardly thin. Venus has the opposite problem, an atmosphere so massive that the useful layer sits above a deadly descent path. Both worlds ask the spacecraft to thread a needle. The needles are different. Venus's needle has a particular shape. The planet's atmosphere is so massive that aero capture, using atmospheric drag to slow the arriving spacecraft, is one of the options mission designers discuss. The atmosphere that might help with braking is the same atmosphere that has to be traversed carefully to reach the usable layer. A spacecraft arriving at the wrong angle, or too fast, or with a deployment sequence that stalls, may not get a second attempt at entering the right altitude band. Mars aerocapture also carries risk, but the target on Mars is the surface, which exists and stays still. The target on Venus, for a mission to an aerial platform, is an altitude layer inside a moving, chemically active atmosphere. Threading the needle means threading it into the right slice of a very deep, very hostile column of gas, and having the platform ready to receive the crew when they arrive there. Stay time is another trap hidden inside distance. A shorter transfer does not automatically mean a shorter total mission. Crewed missions depend on the timing of return windows. Once a crew commits to an interplanetary path, the planets keep moving. A destination may be easy to reach at one moment and hard to leave at another. Some trajectories allow brief stays, others force long waits. Some reduce transit time at the cost of more energy or tighter operations. Some improve one part of the mission while making abort options worse. They remove time from the problem. A human mission is lived in time. Each day in transit adds radiation exposure, equipment wear, and closed environment stress. It also adds medical uncertainty, supply use, maintenance, and psychological load. Each day at the destination adds habitat risk and power demand while life support keeps running. A delayed return window turns distance from a number into a schedule humans must survive. Venus may help some of those numbers under some architectures. It may offer transfer opportunities worth serious attention. But then the architecture asks for atmospheric operations, platform reliability, docking, departure, and rescue in a place humans have never used that way. Mars may punish the crew with longer exposure and surface ascent, but the surface base can be treated as a fixed destination with pre-landed cargo, known sites, and infrastructure that can be improved over multiple missions. The pattern returns. The apparent Venus win is travel geometry. For engineers, this is where the comparison becomes physical. The condition is a mission designed around the upper atmosphere, not the ground. The hidden cost is that getting close to Venus is not the same as safely joining, operating from, and leaving a floating system. Travel time also changes how risk accumulates. A shorter transfer can reduce exposure to deep space radiation and reduce the consumables needed. It can shorten the period when the crew is sealed inside a vehicle with limited repair options. Those gains are real if the architecture earns them, but they can be spent quickly if arrival becomes more delicate or if the return path forces the mission into a long wait. For Mars, many hard days gather around surface systems. Heavy equipment must land, habitats must stay powered, radiation shelters must be made, dust managed, and an ascent vehicle prepared. For Venus, the hard days gather around atmospheric entry and a floating platform. That platform must be captured or deployed, then maintained, docked with, and eventually departed. Both chains can break in different places. The question underneath both is the same. When something breaks, not in theory, but in the middle of a mission with no supply line and no rescue window open for months, which world gives the crew more room to respond? A red warning light inside a habitat is never just a light. It is a question about time. How long before the leak matters? How much power remains? Which valve is stuck? Which spare can be reached? How far away is the backup system? Can the crew isolate the fault, repair it, or wait it out? On Earth, failure often has a background of abundance. Air outside, water somewhere, help on the way, gravity helps, roads help. On Mars and Venus, failure has to be designed before it happens. That is where the word easier becomes most severe. A destination is not easier because it has one friendly number. In the working picture, it is easier only if its failures can be contained or repaired. If they cannot be repaired, they still have to be escaped or survived long enough for the next step. Mars gives a crew a brutal failure environment. The air is too thin to breathe. The cold can kill. Dust can clog, coat, and abrade. Radiation does not pause because a pump failed. low gravity may make every long mission a biological experiment. But Mars gives one mercy. Ground sits under the crew. If a rover breaks, it stops on the ground. If a cargo lander is damaged but intact, it remains where it landed. If a spare part is stored outside, it can sit in the dust. If a pressure problem forces a crew to retreat from one module, another module can in principle be placed some distance away. If a route has been scouted, a rescue rover can drive it. If power systems are separated, one failure may not take all of them at once. None of that is safe in the ordinary sense. A walk between two habitats on Mars would still require a suit and pressure. Heat, communications and time would matter too. A dust storm, terrain problem, or suit malfunction could make a short trip dangerous. But the surface allows separation and return. It gives failure somewhere to stop. A Venus platform changes the question. Gravity is close to Earth's. The atmosphere may provide shielding advantages. Sunlight is stronger. The platform may avoid the surface ascent problem that makes Mars return so heavy. But the condition is flight. The habitat is not only a habitat. At that altitude, it is also the structure that keeps the crew at altitude. If a critical system fails, the fault may not stay local. An envelope problem can become a lift problem, and lift trouble can move quickly into altitude trouble. Once altitude is at risk, temperature and pressure follow. Corrosion may begin on a surface and end as a docking, power or sensor problem. The hidden cost is that survival depends on a machine that cannot simply stop. A Mars habitat can be crippled and still sit on Mars. A Venus platform has to remain a controlled object in an atmosphere. If it loses the ability to hold the right layer, the planet below does not offer a usable refuge. The lower atmosphere is not a bad landing site waiting to be improved. For the crew, it is the reason the whole architecture moved upward in the first place. In practice, this is the cleanest way to understand the failure difference. Outside is deadly on Mars. Below is deadly on Venus too. That does not mean Mars is forgiving. Solar radiation can force the crew into shelter. A rover failure far from base can become a survival crisis. A medical emergency cannot be solved by a quick evacuation to Earth. Mars failure modes are severe, but many of them have a surface logic. The crew can isolate the module, drive the rover, and dig the shelter. They can move supplies, retrieve a spare, and use a backup route. Venus failure modes have an aerial logic. The vehicle must hold altitude, preserve lift, and protect the envelope. It must control drift, keep external mechanisms working, dock in moving air, and prevent descent into worse conditions. Those verbs reveal what has to be made reliable before anyone can call the mission easier. Redundancy becomes different on a floating world. A Mars outpost can separate backup systems across land. It can separate power stations across the site, store supplies in more than one cache, and send a robot to a known coordinate. Even if every part is hard to deliver, once delivered it rests. On a Venus platform, redundancy must be carried and lifted. It must be attached, balanced, protected, or docked. Extra mass is more than inventory. It affects the floating system. Backup systems may need to be airborne too. Spare parts have to survive the same cloud chemistry as the equipment they replace, or remain sealed until use. A rescue element cannot simply park nearby on a plane. During the mission, this is not an argument that rescue is impossible. Rescue becomes architecture, not improvisation. Emergency docking becomes central. A crew in trouble might need another craft to approach a moving platform. That docking system has to work after exposure to cloud conditions. It has to tolerate relative motion, wind, structural limits, and possibly a damaged receiving vehicle. The emergency craft must know where to go, how to match the platform, and what to do if the platform is no longer at the expected altitude. The rescue problem cannot be an afterthought. It must be built into the mission from the beginning. Mars also needs rescue planning from the beginning. A stranded surface crew is a nightmare, and a failed ascent vehicle could trap people. Habitat damage can force impossible choices. A medical crisis can exceed what a small crew can handle. But Mars at least allows the idea of fallback places, a second habitat, a spare rover, a cached emergency supply, a storm shelter, a buried radiation refuge, a known route between assets. For engineers, these are not easy to deliver, but they are understandable once on the ground. Venus must create fallback without ground. Every safe place must also remain afloat or remain reachable from something afloat. The emergency environment is not a terrain. In the working picture, it is a volume of atmosphere with layers, winds, chemistry, and a lethal direction downward. Medical autonomy adds another layer. On either world, a crew cannot count on quick evacuation. An injury during an external repair on Mars may require getting the person back through dust, cold, low pressure, and suit constraints. A failed repair can become a mission-scale problem, but the injured person can be moved toward the habitat. A pressurized rover can drive to their location. The habitat, inadequate as a medical facility, is a fixed structure in a known place. Procedures can take hours. The surface base does not require active management while the rescue is happening. An injury on a Venus platform during an external operation adds a constraint that Mars does not have. The rescue cannot stop the platform from flying. Bringing someone back inside requires an airlock procedure while the vehicle continues to hold altitude. The crew member who goes out to help is working in the same acid-bearing, chemically active environment that caused the problem. Every minute spent on a medical response is a minute the platform's other systems are operating without full crew attention, in a place where reduced attention can become an altitude issue. A medical event is not only a human crisis. At that altitude, it is an operational problem for a vehicle that cannot afford distraction from its primary function of remaining in the correct layer. A crewed Mars ascent vehicle sits on a red plain like a promise that has not been tested yet. It has to wait through dust, cold, and radiation and months of human risk. It has to protect propellant and engines. None of that protection is optional. It has to protect seals, computers, and the people depending on it. Then, at the right time, it has to lift off from another planet and find a spacecraft moving overhead. That is one of the hardest parts of any serious Mars plan. Landing is difficult, living is difficult, but leaving is where the surface stops being a destination and becomes a launch site. Mars gravity is weak compared with Earth's, but it is still gravity. A Mars return vehicle must climb out of a real gravity well. It must do that from a surface where every kilogram matters, where propellant is either brought from Earth, made from local materials, or supported by a long chain of machines that have to work before the crew can trust the ride home. That is why Mars return architecture has always felt heavy, more than physically heavy, decision heavy. If propellant is carried from Earth, the launch mass grows. If propellant is made on Mars, the mission depends on surface industry before people even arrive. If the crew waits for a return window, the stay time stretches. If something fails late, there may be no quick road back. At first, Venus seems to offer a strange relief. A floating platform in the Venusian upper atmosphere does not sit on the furnace surface. It does not need to launch from rock at 467 degrees Celsius and 93 Earth atmospheres of pressure. In practice, it is already high above the place that makes Venus impossible as a normal surface destination. During the mission, this is the part of the comparison that deserves attention. If the destination is an aerial platform near the 50-kilometer region, the return problem is no longer a surface ascent from the bottom of Venus's atmosphere. The crew is not starting from crushed machinery on the ground. They are starting from a layer where pressure and temperature are at least within the range that engineers can discuss without immediately changing the subject. That does not make return easy. It makes return different. The floating outpost has to be more than a place to live. It has to be part of a departure system. Somewhere in that architecture, there has to be a way to get human beings from the platform to a vehicle that can climb, rendezvous, and head home. The vehicle has to survive storage or arrival. It has to meet the platform, or the platform has to meet it. It has to handle the atmosphere around it, the winds moving through it, the chemistry touching it. and the timing of Earth's position far away. The hard image for Mars is a rocket leaving dirt. The hard image for Venus is a rocket leaving air. That sounds gentler until the details arrive. A Mars ascent vehicle can be bolted to a pad. It can be inspected from the ground. Robots can crawl around it. Supplies can be stacked beside it. A habitat can sit nearby. The launch site can be mapped, cleared, and revisited. None of that makes Mars easy, but it gives operations a floor. Tools have a place to rest. For engineers, there is a place for spares. In the working picture, there is a place to park a machine and come back to it tomorrow. A Venus platform has no such ordinary work site. It has altitude and buoyancy, but it also has motion inside a moving atmosphere. It has an outside environment that may be friendlier in pressure than Mars, but far less forgiving in chemistry and control. If a return vehicle is docked to a floating platform, the docking system becomes a lifeline. If it is staged separately, the rendezvous becomes a lifeline. If the crew must transfer through an ascent craft, that craft becomes a lifeline. Each lifeline has to work in a place where the platform itself is part habitat, part aircraft, part pressure system, and part weather survivor. A concept like HAVOC is useful here, but only if it is kept in its proper size. The high-altitude Venus operational concept matters, because it shows that serious engineers have looked at Venus from the air rather than from the ground. It gives the question shape by treating the upper atmosphere as more than a science fiction balcony above a dead planet. It treats that region as a possible mission layer, but a concept study is not a proven transportation system. A concept study can open the departure question, but it cannot close it. It does not prove that a crew can keep the platform healthy, survive emergencies, launch away from it, rendezvous cleanly, and come home. It opens a door without building the hallway. The most tempting sentence would be simple. Venus avoids surface ascent, so Venus return is easier. The evidence is not strong enough for that sentence. Avoiding the surface matters. It may remove one of the most punishing problems Venus would otherwise have. It may make some return designs imaginable that would be impossible from the ground. That constraint is not waiting at the end of the plan. It may let a crew depart from a region where pressure and temperature are not instantly destructive. But Mars has the advantage of an ugly, useful thing: ground. Ground lets infrastructure accumulate. Ground lets a failed rover stop moving. Ground lets a crew build around a problem. Ground lets ascent hardware be delivered and checked. Engineers can bury or cover it, then anchor, warm, shield, and revisit it. It also forces the rocket to climb from the surface, which is a terrible bill to pay. Venus takes away some of that bill and replaces it with another one. The platform must still hold altitude. It must still resist the cloud environment. It must still keep docking systems usable. At that altitude, this is where the comparison becomes physical. It must still give the crew a way out if the main departure path is delayed. It must still answer a question that every crewed destination must answer before romance begins. What happens if leaving is no longer optional? A Mars crew with a damaged ascent vehicle is in deep trouble, but the trouble can be pictured in familiar engineering terms. Repair the vehicle, replace a component, wait for a window, use spare parts, protect the crew in the habitat, try to make the surface base last longer. A Venus crew with a damaged departure system may not have a surface base to fall back on. In that architecture, the platform is the base and the repair yard is the aircraft. The quiet number becomes a working rule. The safe room is still moving through the atmosphere. If altitude control becomes part of the emergency, the problem is not only how to leave later. For the crew, it is how to remain in the survivable layer now. That changes the emotional weight of return. On Mars, return is a mountain of launch mass, propellant, timing, and surface logistics. It demands enormous preparation and a reliable vehicle sitting on reliable ground. Propellant either comes from Earth at enormous launch cost, or is manufactured on Mars using local resources, a process requiring chemical plant equipment to operate reliably before any crew arrives. Neither is simple, but the surface gives the return vehicle somewhere to sit while it waits. An advanced mission can confirm the propellant is ready and the vehicle is healthy before the crew ever leaves Earth. Venus, by placing the crew in the upper atmosphere, removes the surface ascent problem. A departure vehicle could leave from altitude rather than from the furnace below. In practice, that is a genuine reduction in one category of difficulty. But the return vehicle still has to reach the platform, mate with it in a moving atmosphere, and leave at the right time, and all of this happens in an environment that has been working against the platform's external surfaces for the full duration of the mission. The word easier looks small until it has to carry a spacecraft. It can mean less radiation. It can mean warmer temperatures. The point is operational, not decorative. It can mean stronger sunlight. It can mean a shorter trip in one mission design, or a simpler habitat wall, or gravity that treats the human body less strangely. The same word can hide a different kind of advantage. It can also mean a place to set down tools and build a pad. It can mean a place to repair a machine, drill into rock, and launch from something that does not drift. Mars and Venus trade those meanings back and forth. That is why the clean answer is not that Venus is easier than Mars. It is that Venus may be easier in some mission constraints only after the destination is moved off the ground. Once that condition is named, the comparison becomes much more interesting and much less simple. Start with the most basic case. If the question is where humans can stand, Mars wins. That does not mean comfortably or safely. It means Mars can hold the huge chain of equipment the attempt requires. But Mars has a surface that can hold a rover and a lander. It can hold a habitat, a drill and a solar array. It can hold a supply cache and eventually a launch vehicle. Its air is thin, its cold is brutal, its dust is a nuisance and sometimes a threat, and its radiation environment is serious. Still, Mars is a place where machines have worked for years. It has a surface that exploration already knows how to begin using. Venus does not offer that on the ground. The surface is the hard stop, around 467 degrees Celsius, around 93 Earth atmospheres of pressure, a world where ordinary electronics, moving parts, and long-duration surface operations leave the region of normal engineering and enter a much harsher one. In that comparison, there is no clever reversal. Venus is not easier where the rocks are. The argument begins above the rocks, around the high cloud region, near the altitude often discussed around 50 kilometers. The pressure and temperature stop sounding impossible. They do not become Earth. The air cannot be breathed. The clouds are not gentle and the planet below remains lethal. But the numbers shift enough that the mission is no longer a surface base. It becomes an aerial platform. That single move changes the scoreboard. Venus may be easier on pressure and temperature at the destination layer. A habitat floating in that region may not need to hold back near vacuum in quite the same way a Mars habitat does. The outside pressure could be closer to the inside pressure than on Mars. That changes loads and leaks. It also changes structure and emergency thinking, but only if the platform stays in the right layer. Mars has a pressure problem because the atmosphere is too thin. Venus has an altitude problem because the livable discussion exists only within a band. Drop too low and the planet becomes more hostile. The Venus advantage is real only while altitude control is real. Then gravity changes the comparison again. Mars gives humans land at about 0.38 g. That may be workable. It may not be enough for long stays without major health costs. Long-term partial gravity remains one of the large human unknowns. Bones and muscles care about gravity. So do fluid balance and cardiovascular regulation. Balance and medical recovery also care in ways that cannot be dismissed because the scenery looks familiar. Venus gives nearly Earth-like gravity. During the mission, that is one of its strongest advantages. Human bodies would not be living in Mars-level gravity. They would be much closer to the loading they evolved under, for long-duration missions that could matter every hour of every day. But again, the condition arrives immediately. Venus gravity helps only if humans can live on the platform that gives them access to it. Gravity does not repair an acid-damaged seal. It does not rescue a drifting habitat. It does not create a surface refuge. Venus wins the gravity column, but only inside a system that must keep flying. Radiation offers another conditional Venus advantage. Mars has a thin atmosphere, and that means a surface habitat needs serious shielding. Regolith cover and buried shelters become part of survival. So do water walls, storm shelters, careful mission timing, and other design choices. Deep space radiation is not a decoration around the mission. The hazard shapes what a crew can safely do and for how long. A Venus platform would sit within a much thicker atmosphere than Mars can provide. At the right altitude, that atmospheric column may become part of the shield. The planet itself may help block some of what Mars forces the habitat to handle more directly. For engineers, that is a meaningful point for Venus. But it is not a magic word. Radiation depends on altitude and solar events. It also depends on mission duration, habitat design, shielding, and operations. And the same atmosphere that helps shield the crew is also the atmosphere carrying sulfuric acid clouds, strong winds, and the maintenance burden of a floating outpost. Venus may reduce one invisible danger by placing the crew inside a visible one. Power seems to favor Venus too. Venus is closer to the Sun than Earth, and far closer than Mars. Basic sunlight is stronger there. Mars has weaker solar input, dust on panels, seasonal changes, and the possibility of wide dust events that complicate power planning. A floating Venus platform could benefit from that stronger sunlight. But useful power is not the same as available sunlight. Solar arrays have to be placed and protected. They have to be cleaned or designed against cloud chemistry. They have to be kept stable, connected to storage, repaired, and made redundant. Mars has weaker sunlight, but the arrays can sit on land. They can be spread across a site. Robots can service them. Crews can walk or drive to them in suits. A broken panel stays where it fell. On Venus, the power system is part of an aircraft living in an acidic sky. That does not erase the sunlight advantage. It prices it. Distance and travel geometry also resist a simple answer. Venus can come closer to Earth than Mars does, and some mission discussions find attractive opportunities in that inner planet geometry. Shorter or more frequent opportunities could matter. Time in deep space matters. Radiation exposure matters. Supplies matter. Crew isolation matters. But nearest distance is not mission difficulty. A crewed mission has to depart Earth and arrive safely. It has to enter or break into the destination environment, then meet the platform or deploy it. It has to keep the crew alive, keep the system healthy, and leave on a usable path home. Venus may help in some transfer discussions and punish the mission during arrival, platform operations, and departure. Mars may demand a longer surface campaign and a hard ascent, but it also offers land-based staging. The word closer is not large enough to hold all that. What the comparison has really been doing, across every category, is asking the same question in different forms. Not which planet has the better individual numbers, but which planet produces a survivable system when all the numbers are in play at once. A destination that wins 3 columns and loses on maintenance, failure mode management and departure has not won. It has simply described a different set of hard problems. Mars's strongest advantages are almost boring, which is why they can be underestimated. It has ground, rocks, and fixed locations. Machines can stop and wait there. Geology can be touched. Regolith can be moved. Horizons can be mapped. In the working picture that is Mars, stripped of every romantic element, hold that picture beside Venus, and then decide what the comparison is really measuring. The answer has that honest shape. Venus does not become easy by floating above its surface. It becomes newly arguable. Mars does not become obsolete because its familiar picture hides low gravity, radiation, and distance. It remains the world with a more usable working place. The choice is not between a friendly planet and a hostile one. At that altitude, it is between two hostile systems that move their mercy and their danger to different parts of the mission. A small platform hangs in the pale clouds of Venus, far above a surface no human could use. Nothing about that image is simple. The air around it may have pressure and temperature numbers that sound almost familiar. But the world below is still a furnace. Here the clouds still carry chemistry that would touch every seal, panel, window and sensor. The platform survives only by remaining a system that can float, correct itself, make power, dock for repair, and eventually send its crew home. Now place Mars beside it. A habitat sits on a cold red plain under a thin sky. It has ground beneath it, but almost no air around it. Crews can imagine paths, wheels, drills, cables, landing pads, and stored supplies. They must also imagine radiation shielding, dust, deep cold, low gravity, and a return rocket that has to leave at the right time. One world has no ground, the other has almost no atmosphere. That is why the easy answer breaks. Venus is not easier where the rocks are. It only becomes interesting when the destination rises into the upper atmosphere, where pressure, temperature, gravity, sunlight, and atmospheric shielding begin to change the terms. Inside that layer, Venus becomes a serious constraint question rather than a fantasy shortcut. The same move that saves the comparison also creates the cost. A floating outpost is not a valley or a base camp. It is a maintained machine inside a moving, corrosive sky, with no simple refuge below it and no ordinary repair yard outside the door. Mars keeps its own hard truth. It is not a second Earth under a red filter, but it gives exploration a surface, and surfaces matter. They let infrastructure gather. They let machines wait. They let humans point to one place and say, if we survive here, we can add to it. Venus may be easier than Mars in selected mission constraints. Mars may be easier than Venus in selected operational realities. The answer depends on what there means. If there means boots on rock, Mars remains the clearer destination. If there means a pressurized human environment with near-Earth gravity, stronger sunlight, and atmospheric shielding above a lethal planet, Venus deserves a place in the argument, not as the solved world, not as the better world, as the world that exposes how misleading the first picture can be. Humans are not really trying to reach a planet in the simple sense. They are trying to reach a survivable arrangement, a place where the body can last, machines can be maintained, failure has margins, and departure remains possible. On Mars, that arrangement is built against cold, thin air, radiation, dust, and low gravity. On Venus, it would float above heat, pressure, acid, and a surface that cannot save it. That is why this question matters beyond Venus and Mars. A destination is not a photograph. It is a stack of constraints, and every layer has to hold. Mars warns that land is not enough. Venus warns that kinder numbers in one layer do not create a home. Human reach is measured by whether a living system can keep its shape when the planet around it starts taking things away, one margin at a time, with people still inside it.